Thanks for the first presentation. I feel like that's a good segue into now thinking about other modes of travel and public transit. So in this paper, I asked how are the gains from faster public transit networks distributed among rich and poor commuters? How do they vary across cities? Who ultimately benefits from faster public transit? And so there's growing interest in public transit around the world as a tool to reduce road congestion and carbon emissions in cities. Public transportation is also often considered a means of disproportionately targeting welfare improvements for the poor. Billions of dollars are invested in transportation each year, and a large chunk of it goes to mass transit systems. So we need to better understand how effective these transit expansions are going to be at attracting new ridership, substituting drivers on the road, but also where are transit improvements going to be more progressive? Where are expansions going to be more likely to benefit the urban poor? And are the more effective transit improvements also going to be more equitable? So in this paper, I don't study any actual transit expansions. Instead, I study residential location and travel mode choices of high and low income commuters within US cities to identify the heterogeneity in revealed preferences for access to faster transit commutes. Then I can characterize and compare the marginal gains in welfare and transit ridership from counterfactual improvements in a city's mass transit network, and not just the realized ones. And I show how they vary for high and low income commuters and across cities. Now, one of the challenges of translating these location and travel mode choices into preferences for faster commutes is that while surveys can tell us about people's travel times on their observed commutes, we don't know what travel times a commuter would face using a different travel mode or from a different location in the city. So I simulate these unobserved alternative trips on Google Maps and generate travel times faced by commuters from each possible residential location in the city by driving, transit, and walking. And I'm able to study preferences over travel speeds over the same set of trips at the same time of day, on the same day, but for different income groups. Then I develop a discrete choice framework to estimate commuters' willingness to pay for access to faster transit based on their observed location and mode choices, given the choice that they face throughout the city. Then I simulate a 1% increase in transit speeds, let commuters update their choices and evaluate how the gains in transit ridership and welfare compare for different groups. Now, in US cities, public transit expansions are widely believed to benefit the poor and serve as poverty magnets. But studies often find poorer households ride transit more, reside closer to transit stations in typically high density neighborhoods. However, I'm going to show that often it's the richer commuters who tend to sort into the fastest transit commutes within a city, a point that is missed if we focus only on proximity to transit. So who benefits more from faster public transit networks? It's not necessarily the poorer commuters who rely on transit more. So anyways, let me dig into the details and we'll come to results. So I study all metropolitan areas in the US with population over 300,000, where at least 2% of the commutes are by mass public transportation. And when I say mass public transportation, that excludes taxis and ride sharing. And when I talk about cities, they're really metropolitan areas. I'm going to use cities as a shorthand. I rely on the 2006 to 10 American Community Survey for counts of commutes between every possible residence and work neighborhoods within each city. And I have these counts broken down by income bracket and primary travel mode of commuters. And I restrict my study to the universe of workers who commute within the geographic extent of that metropolitan area and who either drive, ride public transit, or walk to work. Then I generate the travel times that would be faced by commuters from each residential location and by each mode of travel, using data from trips that I simulate on Google Maps. And these encompass millions of trips, all queried on Google Maps over the same weekday and at the same departure times by each of the travel modes. Google predicts travel times on these trips based on their historical as well as live tracking of the movement of smartphones. And in other papers, I find that Google's predictions tend to credibly capture the variation in travel time from real driving trips. For public transit, travel time predictions often are also based on schedules shared by transit authorities or crowdsourced general transit fleet specification. And these travel times include waits between transfers, as well as time spent walking to transit stops. For trips with no viable transit routes, Google returns the predicted walking times. And since transit availability and frequency are sensitive to the departure time, I query each trip at different times of the day and consider a weighted average of the travel times based on what the observed departure times are in travel surveys. And the travel times incorporate both the velocity on the road as well as the directness of the travel route. So a faster transit commute could be due to a route with few detours, less time spent walking to the stop or waiting at the stop. It could also be due to a route with fewer stops or with a subway or dedicated bus lane. So travel time between an origin and destination then is essentially the trip distance divided by a mode-specific travel speed. And given distances are fixed between locations, the policy-relevant measure of interest that infrastructure investments are going to seek to change is really this mode-specific speed. That is, how well does the transit or driving network connect to neighborhoods? So while we care about travel times, we're going to affect it through speed. And that's what I'm going to focus on here. Okay, so let me show you what transit ridership looks like across commutes within cities. The likelihood of riding transit depends on transit speed relative to driving between the origin destination pair. And here I plot the probability of riding transit as a function of the driving speed on the vertical axis and the transit speed, the transit speed on the vertical axis and the driving speed on the horizontal axis. And I pull together commutes across all cities. I standardize the transit and driving speeds. So we're really looking at the variation in speeds within cities. And the colors indicate average transit ridership. We can see right away that conditional on driving speed, transit ridership is higher on commutes where transit is fast. Conditional on transit speed, transit ridership is higher on commutes where driving is slow. As such, transit and driving are substitutes. Commuters choose more of the one when travel is costlier on the other in terms of speed. The income composition of transit riders also varies systematically over travel speeds. Higher income transit riders are more likely to dominate faster commuting routes. Replicating this graph for drivers, we see a similar pattern. Higher income drivers tend to be sorted into faster driving routes, while lower income drivers tend to be sorted into slower driving routes, though the sorting is perhaps less aggressive than for transit riders. Again, these figures are just raw correlations, potentially driven by other spatial attributes. So let me propose an empirical framework to isolate the extent to which the income sorting reflects preferences for faster commutes. So let's consider a city with a fixed population of commuters with different incomes. There's a fixed set of residential neighborhoods and work locations and 3 modes of travel. These commuters either drive, ride the transit, or walk. There's a competitive housing market that determines housing prices, that captures this demand for residential locations. Commuters, given their work location and income, they choose the residential neighborhood to live in and their mode of travel to work. And they do so to maximize their preferences over commuting times, housing costs, and other mode and neighborhood attributes. So the utility function, so these preferences are captured by a utility function, which reflects both commuters' preferences over distance, so proximity to work, as well as the mode-specific speed to work, which also reflects sort of differences in the value of time, so and income-specific differences in preferences for modes and other things. Then there is a price and income elastic housing consumption, which reflects that sort of housing demand could vary across incomes, and that could drive the sorting behavior as well. There's a mode, neighborhood, and income fix effect, which incorporates any sort of income sorting on travel mode characteristics, like bus fares or cost of owning cars, as well as neighborhood amenities, as well as sort of spatial attributes of travel modes, like variation in parking and sort of access to non-commuting destinations. And an error term that captures idiosyncratic preferences, and I'm going to assume that follows an extreme value distribution. Okay. So I estimate this in 2 stages. I estimate this housing demand function, and then I estimate separate coefficients for the preferences over speed and distance. and these fixed effects by mode, neighborhood, and income. And I do so to maximize the likelihood that commuters, given their choice set of prices across neighborhoods and modes, they're choosing the one, they maximize the likelihood of choosing the observed neighborhood and mode that they live in. And I do so numerically, and I estimate separate coefficients for each city, travel mode, and income group. And I'm going to present it in terms of their willingness to pay for higher commuting speed in terms of housing prices, so in terms of how much you're willing to pay in housing prices for access to faster commutes. Okay, so let me first present my results in terms of the willingness to pay conditional on your travel mode choice. And I can decompose these estimates by commuters' income bracket. First, let's just look at the two largest cities in my sample, New York and Los Angeles. As we move from left to right on this table, note that richer commuters have higher willingness to pay for faster commutes than poorer commuters. This is true both for transit riders and drivers. Transit riders with annual incomes over $75,000 are willing to pay over 3 to 5 times more for a 1% increase in commuting speed than transit riders with incomes below $35,000. And this isn't actually just true in New York and Los Angeles, but let me also show you sort of what the marginal willingness to ride transit looks like in response to a faster transit network. When I increase travel speeds by 1% along a city's entire mass transit network, what fraction of commuters switch to riding transit? And I compute these average gains in ridership by income bracket again, and I see very different outcomes across cities. As before, let me use New York and Los Angeles as examples. As an increase in transit speeds in New York leads to larger gains in transit ridership among the highest income commuters than among the lower income commuters. In contrast, a faster transit network in Los Angeles leads to larger gains in ridership among lower income commuters than higher income commuters. And this is not as surprising as it may seem at first. In New York, public transit is a lot faster, baseline transit ridership is higher. So given that higher income commuters have a higher willingness to pay for faster commutes, improvements in transit speed are more likely to get high income drivers to switch to riding transit when transit is fast relative to driving, but less so when transit is slow. Whereas lower income commuters have relatively lower willingness to pay for faster commutes and are more likely to choose the cheaper rather than the faster mode of travel. So they're less responsive to changes, improvements in travel speeds. So while I don't have time to show you these results for other cities, but the case of New York and Los Angeles are quite generalizable. Cities where transit is fast and where ridership is high are those where improvements in transit are more likely to attract high income commuters. Now, what does that mean for the distribution of welfare gains across high and low income commuters? Previously, I characterized this marginal willingness to pay for faster commutes and this marginal willingness to ride transit. Let me now present their unconditional marginal willingness to pay for faster transit. And here I rank the cities in my sample in the descending order of overall gains from transit improvements across all commuters. San Francisco has the highest willingness to pay for a faster transit network, but it's also where the gains accrue more to higher income commuters, almost 3 times more. We see this hold for New York, Boston, DC, and Chicago too. But the differences across income brackets get smaller as I move down the list. In fact, outside of these popular high-speed transit cities, poorer commuters are the ones to benefit relatively more from faster transit networks. And increasingly so in cities where transit is slower and overall gains from transit improvements are smaller. For instance, in Portland, it's the poorest commuters who have a willingness to pay that is 3 times higher than that of the rich. And from the perspective of a social planner, you can see that there are strong incentives to target transit improvements in cities like San Francisco and New York, where driving is relatively slow and transit is popular enough that transit expansions would attract a lot of new ridership and help tackle congestion, pollution, and other externalities of driving. But these are also the cities where transit improvements are relatively less likely to benefit the poor and those who rely on transit more. And these numbers have important implications at the margin. For instance, transit fares tend to be fixed across buses and subways and across space, which means low transit fares end up mainly being subsidies to the rich in fast transit cities like San Francisco. Given higher income commuters have higher willingness to pay for fast transit, planners could potentially charge higher fares on subways and rail transit, or along more popular fast transit routes, and lower fares on buses to subsidize transit more effectively for those who rely on it more. Welfare also depends on who bears the cost of transit. So perhaps transit improvements to fast transit cities could benefit from more progressive means of revenue generation. So anyway, so far I can only show you sort of what it looks like in the current state of the world. But these have important implications for how we may want to think about how to distribute transit or how to price it. So thank you, and I'll leave it here.
Thanks so much. This is really interesting stuff. I remind everyone in the audience again, if you put your questions into the Q&A or the chat, that'll give me a quick way to bring them out when we get to this brief question and answer period at the end. I didn't see any. I hope I'm not just missing them. But since I didn't see them, I'll ask one that was on my mind this whole time. This shows my bias as a college professor because we're obsessed with parking. What about the costs of parking? Is that something that could be included also in this and make a difference in this choice between who's going to drive and who's going to take transit?
Yeah, absolutely. Yeah. So I think what I've mostly focused on is the cost of travel in terms of travel time, in terms of travel speed. But there are also these other sort of there are many different costs to travel which vary across travel modes, and sort of different income groups would respond to differently. And parking is another sort of thing that varies across place. The pricing of parking is also something that varies across place, and it could actually be a tool that we can use to to sort of subsidize particular income groups or sort of redistribute the gains from faster travel. So definitely that would be an interesting tool to look at as well.